In today's video, we shall take a closer look at the topic of conservation of energy. Energy comes in different forms. To name a few: potential energy, kinetic energy. These two belongs to the type of energy known as mechanical energy. And then you have energy in a form of heat, chemical energy, nuclear energy, and so on. So what is exactly the principle of conservation of energy? Let's look at a system. And this system initially is in the initial state. Let's call that state I. Let's assume the amount of total energy the system has in that state is EI. Then the system evolves to some final state in which its energy there, the total energy is E sub F. EI and EF can and may include all the forms of energy that we have just introduced. The principle of conservation of energy states EI equals EF. The energy of the system is conserved, and there is no loss in the energy. Let's look at a couple of examples. Example 1. Let's assume you have an object that is thrown upward from some point, which we call the initial point. And this point is at some height, let's call it HI, from the ground. So this is the ground. The speed of that object at that point is VI. So this object travels to some other point, which is at some other height, and that point is the final point. Let's assume the height is HF, and at that final point, the object is moving with a speed, let's say, VF. So let's assume there is no air drag of any kind to stop or to impede the motion of this object. So let's see how the principle of conservation of energy works here. What is the total energy of this object when the object is at the initial point? There are two forms. If you assume the mass of the object is m, we know the object is moving, so definitely it has kinetic energy given by half mvi squared. Now it is also at some elevated height. I'm going to assume that the gravitational potential energy at the ground is the 0 joule level. So that means at a higher point, namely at the initial point, the gravitational potential energy of this object, Earth system, is simply m times gravitational acceleration times hi. And that is it. We don't have any other forms of energy. We assume that there aren't any other forms of energy left. Now let's look at the final point. At the final point, the total energy also consists of two forms. One is the kinetic energy, half mvf squared, where vf is the speed of the object at the final point, and its gravitational potential energy, namely the gravitational potential energy of the object Earth system at that point, is mghf. Now the conservation of energy states, since you don't have any losses due to air drag or any kind of friction, then EI equals EF. So since these two forms of energy are known as the mechanical energy, we say the mechanical energy of the system is conserved. Or what you have here is conservation of mechanical energy in action. One application of this equation is to determine an unknown parameter. Let's say you are given HI, HF, and VF. We want to determine VI. You can certainly do that from these two expressions. Example 2. Let's assume you have an inclined plane, as shown in this figure, and you have an object starting from at some elevated position, which we can call the initial position, and it slides all the way down to the bottom of that inclined plane, and that position can be labeled as the final position. Let's say like that. However, now this inclined plane is rough, so you have friction associated with it. In this case, since the object is moving, you have kinetic friction associated with this. Let's assume the height of the initial position of the object is hi, and the final location is at the bottom of that inclined plane, so that means the final height is 0. And let's assume that the length of that inclined plane is d. So let's write down the total energy of this object at the initial location, namely at that location. We can take the ground level to be the level where the gravitational potential energy is 0. So that means the gravitational potential energy of that object, Earth system, is the mass of the object, let's assume the mass is m, times gravitational acceleration times hi. And then it also has kinetic energy because it's moving with some speed. Let's assume it's moving with vi. So the kinetic energy is half m vi squared. Now let's look at the final position of the object, namely at the bottom of that inclined plane. There is no height, so that means the gravitational potential energy of the system is 0. It is still moving with some speed, let's call that speed vf, so it has kinetic energy, half m vf squared. One other thing to note is that as the object is sliding down, it is subjected to kinetic friction opposing the motion. That means this kinetic friction is doing some work as the object slides the entire distance d. The magnitude of work done by friction is the kinetic friction times the distance the friction acts. So this is the magnitude of the work done by that kinetic friction. In this example, obviously, since there is some kind of loss due to friction, EI can never be the same as EF. Indeed, EI is greater than EF. The object starts with an amount of energy, EI, or an amount of mechanical energy, EI, that is greater than the mechanical energy at the bottom of the plane, EF. So what accounts for the difference? The difference is that work done by the friction. So when you take EI minus EF, you get WF. So this corresponds to the reduction in the mechanical energy of this object as it slides down from the initial location to the final location at the bottom of the plane. It must be stressed that conservation of energy holds true. What did not hold here in this case is conservation of mechanical energy because of the presence of friction force. Indeed, this expression here is a reflection of conservation of energy, whereas this expression shows conservation of mechanical energy does not hold in this particular case because of the presence of friction. Let's look at the following example. A 30 kg child slides from rest 10 meters down a pine tree, moving with a speed of 4 meters per second just before hitting the ground. Find the change in the gravitational potential energy of the child Earth system during the slide. So that is the tree, and the child is sliding downward. So this is the initial position. Let's assume that is the final position. At the initial location, the speed of movement is 0, there's no movement. At the final location, the speed is 4 meters per second, and the difference in height is 4 meters. So to answer part A, we can take the bottom position to be the position where the gravitational potential energy of the system is 0. So the change in gravitational potential energy of the Earth child or child Earth system is quite simply the mass of the child, which is 30 times gravitational acceleration, g, times the height, 4, measured from the level where the gravitational potential energy is 0. And that's going to give you 1,177 joules. Now let's do part B, the kinetic energy of the child just before it hits the ground. The kinetic energy just before the child hit the ground means the final kinetic energy, the kinetic energy at the final point. So half times the mass, 30, times the speed there, which is 4, squared. And that's going to be 240 joules. What does that mean? That means the mechanical energy at the initial location is given by the gravitational potential energy of the system when the object is there, namely when the child is there, plus the kinetic energy there. We know the kinetic energy there is 0 because the object or the child slides from rest. So the potential energy there is 1177 joules as determined in part A. Now what about the energy at the final location? At the final location, the gravitational potential energy of the system was set to be 0. So that is 0. The kinetic energy there has been determined in part B. It's 240 joules. Now as you can see, the initial mechanical energy is much greater than the final mechanical energy. So there is some kind of loss involved. And that loss, EI minus EF, is about 937 joules. So this 937 joules would enable us to answer part C, namely what is the average frictional force that acts on the sliding child. So for part C, we know the difference in the two energies, namely 937, is due to the work done by friction. As the object or the child is sliding down, the friction is moving in an opposite direction. And the friction acts for a distance of 4 meters. So friction times 4, this is the work done by friction, equals 937. So the average friction is therefore 937 divided by 4 newtons, which will give you 234 newtons as the answer. And that's the answer for part C. And that solves the problem. Problem 2. An 80-gram ball is thrown from point 1.2 meters above the ground with speed 15 meters per second. So let's say the first point, the initial point, is there, 1.2 meters, and the speed there is 15 meters per second. When it reaches the height of 2.4 meters, its speed is 10 meters per second. So let's say at that point, that is the final point, its speed is, let's say, 10 meters per second. The height is 2.4 meters. Find the reduction in the mechanical energy of the ball-earth system due to air drag. So let's determine the mechanical energy at the initial location. So the potential energy can be taken to be 0 there. So over there, the mass is 80 grams, so 0.08 kg. Times gravitational acceleration times 1.2, plus the kinetic energy is half times the mass 0.08 kg, and the speed is 15, so 15 squared. So this entire thing is the mechanical energy at the initial location. Now the final point, the mechanical energy there, the gravitational potential energy 0.08 times gravity times 2.4. Now the height is 2.4. The kinetic energy there is half times 0.08, which is the mass, times 10 squared. Together it's joules. So the reduction is given by EI minus EF, and that's going to be 4.06 joules. So this is the amount of work done by the air drag on this ball as it moves from the initial position to the final position. As always, thank you for watching.